Hello and welcome to this webinar on designing supervisory logic for safety critical systems. Before we get started, I wanted us to spend a couple of minutes familiarizing ourselves with the system that we will be designing. It's a redundant cooling system. Let's go into Simulink and look at what the design looks like. You're looking at the Simulink editor at this point. The editor contains the redundant cooling system. It has three parts. The first part is this block in green. This is the part of which we call the control logic. It's the part of the design that gets implemented onto your controller. It controls the cooling system. The cooling system contains power supplies and associated cooling fans. And the controller also controls a device that is generating heat. An example of this device would be the control rods in a nuclear power plant. The goal of this control logic is to maintain the temperature of this device below a threshold. And if it cannot do that because maybe the cooling systems fail or because the device is generating too much heat, it is supposed to handle those faults and shut down the complete system safely. So the reason we picked this particular example is because it has the key elements of a redundant safety critical system. We also have some buttons on the left-hand side. These are used for injecting faults during simulation within your system over here, or your cooling system over here. So our goal is how to design, test, and verify the control logic. So let's look at the control logic. It's designed using Stateflow, which is an environment for designing state machines. So here you're looking at state machines. On the left-hand side is the logic for the device within this box on the left-hand side. The device has two states, running or shut down. And there are arrows that actually model transition paths between these states. The functions or the conditions on these transitions actually decide whether these transitions should be taken and when they should be taken. There are two cooling systems, on the right-hand side, cooling system A and cooling system B. Let's look at cooling systems. A, it has two parts, the power supply logic and the fan logic. So the power supply, which is within this left-hand side box, has three modes, off, on, and isolated. Similarly, the fan logic has three modes, off, running, and isolated, with transitions going between them, as I said, deciding when the modes should be shifted. So let's quickly simulate the system and see how it behaves. Okay, so we looked at the design. Let's simulate it by hitting the Run button in the Simulink editor. By hitting the Run button, the Simulink engine in the background is going to calculate how the system is going to behave and the outputs at every simulation time. The modes of the system that are active at any point in time are highlighted using this blue outline in state machines. So you can see that when I look at the power supply logic, its on mode is active. Similarly, when I go to fan logic, the running mode is active. Okay. Now, if I were to inject a fault in the power supply system, by clicking on this button, you will see a mode switch within both these systems. So you go from the on state to the isolated and from running to off for the fan. Okay. So this is an example of a system that we will look at how to design, test, and verify. Let me get back to our presentation. So, who are you really talking to? I'm Siddharth. I am product marketing manager at the MathWorks. I've been at the MathWorks for about 7 years. Was a software developer before that, and have a background in mechanical engineering. I got a master's from Worcester Polytechnic. And my co-presenter here is Nishat. Nishat, could you introduce yourself?
Thank you, Siddharth. My name is Nishat Wasi. I'm the product marketing manager for verification and validation tools at the MathWorks. And together with Siddharth, we welcome you to this webinar, and we'd be happy to answer any questions you have on the same. Back to you, Siddharth.
Thanks. So before we actually jump into the tools and the things that the capabilities that we're going to, the workflow we're going to talk about today, I want us to take a minute or two to understand what we mean by supervisory logic over here. So a Wikipedia definition of supervisory control is that it's a general term for control of many individual controllers or control loops. In other words, You can think of supervisory control as a layer of control that lies above your closed loop control, and it actually activates and deactivates the closed loop control when needed. It is also responsible for startup, safe operation, and shutdown of the device. So in some way, it's actually more important to make sure that the safety critical part of the system, which is the supervisory control, is functioning how it should. Now, you'd come across supervisory control in a variety of applications. Almost in every system that is safety critical, you will come across that. Think about medical applications, plants, industrial and machinery, robotics, packaging equipment, or in the transportation industry. Look at a signaling system. They all contain some sort of logic to shut down the device and make sure that it is running properly, so that you're actually not damaging equipment, or even worse, not causing damage to human life around you. When things go wrong with supervisory control, they generally have very catastrophic consequences. So our goal today in the workflow that we're going to show you is to walk through some capabilities that will help you design a lot of this logic on the desktop before any hardware is available. And then we'll show you how to add rigor and use some mathematical techniques to actually make sure that the system is behaving how it should. So we've roughly broken up our presentation into 3 parts. The first is we'll talk about how to model. Second is we'll talk about how to verify, as I said. And the end, we'll generate code so that you can deploy that code onto either your hardware prototype or onto your final production hardware so that you can test it. Okay? So let's get into the modeling portion. So as I said, we're going to focus on the control logic portion, which is the green portion. When I double click on that, that brings me to this other window which has this block in the middle. This block is what comes with Stateflow. So Stateflow is an environment for modeling state machines, but it also provides ways to do truth tables, flowcharts, and state transition tables. When you double click on this block, it is going to take you within the Stateflow editor. So with the Stateflow editor, you get a canvas in the middle within which you can draw these state machines. But you also get these objects on the left-hand side, which are the building blocks of state machines. So like states, junctions, transitions, and other objects.
So Siddharth, I see some dashed lines and then I see some solid lines as states. Is there a significance to this?
Right, that's a good question. So all these rectangles that you're seeing over here are essentially states or the modes of the system. The dashed lines, at least the same level of hierarchy, are the states that need to be executed at every time step or in parallel. So essentially, for example, the device needs to be active at the same time as the cooling systems. But if you look within the device, it is either in the running mode or the shutdown mode, not in both of them together, right? So those solid lines show exclusive states. You're either in this or the other, and the dashed lines show what you're active at simultaneously. Similarly, the logic for cooling system A and B need to be evaluated at the same time. So the reason we've used Stateflow for modeling supervisory control over here is because it's a very natural way to represent modes of a system. Each mode gets represented as a state, and the paths for when to switch between them are shown using these transitions. The other things that I wanted to point out were these conditions that are written on each of these transitions. They can either just be Boolean conditions, or they can be functions that are written. They can be, as I said, truth tables in the beginning, as I had pointed out, or they can be flowcharts, like I'm showing over here. You could also do this using other kinds of environments like Simulink or MATLAB, and you can write it in C code as well, but it's not as elegant, and you have to do a lot of low-level bookkeeping to be writing these modes out. With Stateflow, a lot of that gets taken away. It's a very intuitive and high-level graphical way of understanding and representing the logic, where you don't have to do the low-level bookkeeping that comes with representing it, using it in modeling it in any other format.
And Siddharth, is it okay to say that basically it's integrated into Simulink as well, right? So this works it's basically an integration platform to build your logic. That's
a good point. Yes. So it does fit within the Simulink's environment. As I said, when I go one level higher within my model, this is my Stateflow design. It sits within the Simulink editor, which I can go further up and look at my complete design. So we think of this as we're going down layers within our design, right? Functions calling subfunctions within it. So here I go within this, I look at the Stateflow component, with further within it actually is looking at the Stateflow design. Same way within Stateflow, you have hierarchy as well, as I said. Now this box is covering the logic for devices. Everything within it is a logic for a device. If I go within the cooling system A, within the system now, I have the logic for the cooling system, which is further consists of the power supply and the fan logic, as I talked about in the beginning. So there is the editor, along with providing the, as I said, some of the, as a canvas to draw it, it also provides some edit time checks for you. So let's say you were to actually mistakenly have some semantic errors by drawing one state over the other, or the states weren't properly aligned. This would actually get automatically flagged to you, as I'm showing you over here in Stateflow as red. But you would also have lines to actually help you align these objects and make sure that the logic is that the objects are actually aligning up as they should. So there are other static and runtime checks that are provided with the tool. There's automatic completion for new users to help for those who are unfamiliar with state machine syntax on how you can actually, what syntax would be needed to actually build these systems up. But that's outside the scope of what we can cover today. But just to say, it's a fairly sophisticated design environment for building state machines. I talked about what the editor provides in terms of when you're modeling the state machines. The other aspect is when you're actually simulating. Generally, when I'm simulating a system, and if something doesn't work how it should, I need to debug it. And there's a fair amount of capability that this environment provides for debugging as well. So as a simple example, when I look at this transition that goes between the on and the isolated state, if I wanted to hone in on what happens and when is this transition taken, what are the values of my variables, I can set a breakpoint on this. And I do that, I can set up one of two kinds of breakpoints, either when this arrow is valid or when it is tested. So I'm going to set a breakpoint on when it is valid. Let me now actually run my simulation and get to a point where I will actually excite this particular transition. Okay, so I'm at a point where I'm going to run my simulation again. And as I start my simulation, you can see that I'm in cooling system A, which contains logic for power supply logic for the power supply system. And there my on state is active. For me to get into the isolated state, I need some sort of error. So I'm going to do that by interactively creating an error within my system. When I do that, you can see that my simulation at this point is stopped over here. You can see this green arrow, which is showing that my simulation has stopped. You can see the simulation is stopped at 97 seconds.
So Siddharth, can you go back and forth in this as well? Since you're in debug mode, is there any mechanism to help you, step in and do more with this?
That's a good point. So not only do you get this debugging capability, as in these breakpoints, but you get a bunch of other buttons on the top as well for more fine-grained debugging. So you can step in, step over, step out of functions as you're debugging. You can step forward like this over here, but you can also step back. So this brings up my stepping back capabilities. I can enable them. And I won't get into the all the properties over here, but essentially what I can do is if I step forward, and if you keep your eyes on the simulation time here, see I'm at 98 seconds. I get to 98.5, I get to 99, and now I can hit back and get to 98.5, 98 seconds. So this is very useful when you're debugging. If you want to zero in on a particular time step, so like a DVR, you can also go forward, but also go backward and see what exactly was happening at that time step. And as you might have already noticed, when you're debugging, you also get these tooltips that are telling you the values of data for different states. So I'm looking at what are the values of variables, which again becomes quite useful when you're debugging, right? Okay, that's what I wanted to cover in terms of debugging. So let's stop this. But as a designer, I mean, the start of any such design generally is some sort of requirements document. So I would have my requirements either coming in Word or in Excel or in some format. And that would form the basis of the model that I'm designing. Now, within our tools, within this editor, you can actually link those requirements with these parts of the model. What I mean by that is, let's say I want to see what requirement was the basis of the creation of this particular design component. I can right click on it and I can see that it was created to implement a requirement which said modes of operation of the power supply are off, on, and isolated. So not only is this a static requirement over here, if I click on it, it actually, the link that I've created actually opens up the Word document and highlights the requirement that was in Word. Similarly, I can go back from the Word document to the appropriate design element as well. So as I clicked on that link over here, you can see that the appropriate design element within Stateflow was opened up. So this is exceptionally useful when debugging as well. If something isn't behaving how it should, you want to go back to your requirements and then see, am I implementing my design right? Am I doing things right? I mean, and basically go and debug that. The other place when requirements thinking becomes extremely important is when your requirements change. So now that you know what parts of your design are affected by your requirements, you know what needs to change when a particular requirement changes.
Right. I mean, you can not only within the project, but within teams as well, right? If you want to figure out how many people does this change in requirement take to implement, right? I mean, basically trying to associate cost even with the requirement change.
Exactly. So as I'm a designer, I've created some sort of, as I'm building these models, I'm exciting with some sort of ad hoc sort of inputs, right? To see that the design is going down the path that I want, the conditions are sort of written well. The other thing that I could do is place it within a closed loop system, as I did over here, and try to inject faults by clicking on these buttons and seeing if my plant actually breaks or some other errors are caused. What really happens within this logic and how does it behave? So that's some sort of ad hoc testing that I'm doing to make sure that the logic sort of works all right. And let's say all my ad hoc testing gets through. I don't know, it just seems that isn't the point when I can stop for a safety critical system, even though it seems like from a high level, I've excited most of my transitions. I've written test cases to do some sort of stuff, but it's not really clear. Is this the end of my testing? Nishad, if I was designing a safety critical system, what more should I be doing? Is this the right time to stop, or should I be doing more?
No, great segue, Siddharth. I think this is a great starting point, right? We started off with design. We started off with requirements. You've not only designed and simulated the behavior of your model, or in our case, this state flow chart, but you've also, injected faults and seen how the faults go through and whether we've designed or got our requirements right? But you can do more, right? You want to enhance the robustness of your design. You want to do more to test this design off. And I'm going to go through some of the mechanisms within model verification, which will enhance design robustness. So to start off, I am going to get out of presentation mode and navigate back into the Simulink environment. What I have here is a test harness setup. In the center, I have my design under test, which is the control logic. This is what Siddharth talked about and showed you how we're designing our supervisory mode logic. On the left-hand side, I have my inputs and expected results, which I am driving the system with. And on the right, I have my comparison to expected behavior. So let me open up what this input block looks like. In my case, it's a signal builder. And you can see I have set this up to have 4 test cases. Each of these tests are linked to a particular requirement, right? This is a requirement. This is the same requirement document which Siddharth showed you for his design. Again, the pretext is I have a set of requirements, right? I have my design based on the requirements, and I also have tests which I have written for those requirements.
So these requirements that you have, I had a Word document. Similarly, I mean, I'm sure there are other formats that you can go and link as well. What formats can you support for requirements for linking here?
That's a great question. Let me bring up the details of this particular requirement, right? As you mentioned, we're using Microsoft Word. Out of the box, the tool will support Word, Excel, PDF, IBM Rational Doors, and we have an API which you can use to or you can basically link to your custom file format. So say, I work at company X and I have a particular file format which only my team uses. I can use this API to link to such requirement docs as well, or requirement documents as well.
And it's the same list of objects that you can link from within a Stateflow editor or Simulink editor as well.
Absolutely. I mean, you can drill down from a block level, subsystem level, or even transition level in Stateflow. And in this case, I'm linking to test cases and test suites, right? I also have some assertions set up. So I am comparing my simulation outputs to expected behavior. Again, these are a bunch of blocks, basically comparison of simulation outputs to expected behavior, right?
So essentially what this is doing is that the assertion block is, it's sort of a block that throws a flag, right? If there is something that, if the outputs don't match, I can either have it throw an error, I can actually have it stop the simulation, I can attach a callback, I can do anything, many sophisticated things to actually analyze what went wrong and what's the point where my outputs didn't match.
Absolutely. And in my particular case, I'd set it up to stop my simulation if there's any incorrect result, right? Okay. So again, this is step one of model verification, right?
So one more question, right, before we move on from this. So these test cases that you've written, you talked about Model Builder, but what other formats could this be sort of be sitting within? I mean, could I be getting these test cases from some other format? I know our customers generally start from Excel or some format like that.
You're right. That's a great point. I have used Signal Builder over here to manually create these tests. I've done this by hand, but we have a lot of customers who use Excel or CSV files even to write up test cases. The tool allows you to import from files. So basically it's importing from a test written outside of MATLAB and Simulink, gets it into this environment and sets this up for you. So yes, to answer your question, you can use Excel and CSV formats. You can even get data into the base MATLAB workspace, and we'll be able to leverage that as test cases as well.
Excellent.
All right. So, in our particular case, I went through, ran these tests, and everything passed. I got no failures from a functional or input-output behavior perspective. I'm in a good shape. But the question remains, right, is this good enough?
And I think the main point that I want to highlight is that we're still in simulation mode. So we started at a high level, right? We built our stateflow machine, our stateflow logic. We simulated it to see that it is doing the right things with its animation. We debugged it, made sure that the inputs were all right. We did interactive testing. Then we put it in a harness. We excited it with all the inputs, but it's still in simulation. You don't have any hardware. You haven't had to depend on any hardware to create and test to this level of the algorithm. Is that right?
Right. Absolutely. But the question still remains, right? Is this enough? Right. When I started off with tests which were created or based out of requirements, right? What if my requirements were incomplete? What if there were derived requirements which I'm not thinking about, right? Is there anything else which I can do at a model level to increase and enhance robustness of this control logic? In our particular case, I've used structural verification techniques to test the thoroughness, or basically to figure out how thoroughly my test cases have executed my design, right? I use a metric called model coverage. Let me show you, right? This is my control unit, right? And I have run my 4 test cases, again, requirements-based test cases on this model, and I'm collecting what I call coverage metrics, right? The tool will analyze decision and condition points within my mode logic, in our case state flow chart. Like condition points would be something like an if, right? I'm transitioning from state A to state B. That would be and there's a condition associated with that transition, right? The tool has figured out that there are 104 such conditions within my state flow chart, out of which my 4 test cases are able to test 87% of these, or 90 out of 104, right? So again, my 4 test cases are able to go through certain parts of my design, but not all.
I'm also seeing some colors here. What do the colors mean?
It's great you bring that in. So green indicates I've got full coverage for this transition from running to shutdown mode of operation. Red, on the other hand, indicates that reset error was never true. So I have only partial coverage for transitioning from shutdown state to running mode of operation. Gray indicates basically parts which were filtered from coverage, or basically shutdown does not have any condition or decision points within it. That's why it shows up as gray. So that's again, this gives you an idea of how thoroughly your tests are going through your model and exercising different portions of your model.
So if I don't excite something in my design, should I be worried?
That's a good point. You definitely want all parts of your design to be tested. You want to thoroughly test your supervisory control, right? And back to why you want to do this. You want to ensure that there's nothing which was not a requirement. There's something, because if this is going to really control a nuclear application or some other safety critical or high integrity application, you really don't want untested parts of your design to exist, right? So, what do I do next, right? I have these parts in red, and red means not that great. You want to have test cases for this. I have two options. One, I can go and manually write these test cases, just like the way I did in Signal Builder in my harness model, which I showed you earlier. Or I can use mathematical techniques to generate these test cases for me. In our case, I'm going to use Simulink Design Verifier to generate tests for this particular model. And very similar to what we looked at before, right? In terms of coverage objectives, the first step which this tool will do is it will go through my model and figure out, okay, how many condition and decision points can exist for this particular state flow chart, right? And then it will go one by one and try to figure out, how do I write a test case which will execute that condition and exercise that decision point, right? So it finds 257 different objectives. I'm going to highlight the analysis result in the model to go through these in detail.
So again, I understood what it meant for model coverage, but what are the color that you're showing? It has a red outline, and I'm sure if you go inside the state machine, it'll still have those colors. What do the colors mean now?
Right. So let's pick an example. Okay, I'm picking on reset error over here. Let me zoom in on this. What the analysis results show you, right? Again, we've mathematically gone through and we are creating test cases which will make this particular condition reset error true and which will make it false, right? As you can see, there are quick links, hyperlinks over here to test cases. Let me go ahead and click on those. What this will do is it will bring up a new harness model, a new test harness model for me. And in that new, let me minimize this. Okay. We bring it up on the side over here for you. Again, this is something which is automatically generated for you. You have your design under test, which is the mode logic. This is the input, which is Signal Builder in our case, right? And by clicking on that hyperlink, it is going to identify the exact test case, which will execute that reset error condition. You'll notice that, we've automatically generated 39 test cases for you for this particular model. And basically, coming back to your question, right? What was green? Green indicates the tool was able to mathematically create a test case to execute that particular condition, right? I can highlight analysis results again, take you back into the model, right? And then just to think about what you do with this test case, right? These test cases which were generated or created for you, you could very well reuse these test cases in software in the loop simulations, in hardware. Take this out of the MATLAB and Simulink environment, take it into your hardware. We allow you to export these as well. So you could use it as regression testing mechanisms as well.
So these test cases that you've written, right? I had some requirements-based tests that I started with that were taking the functionality, and now I have this separate set of test cases, the 39 or 40. Is there a way to build on what I already have, or do I always have to start from scratch and build everything up again?
Well, that's a great question. So a lot of our customers do exactly what you asked, right? We start with requirements-based tests, and you can give these tests to the tool and ask this tool to build on existing test vectors which you have. So you can absolutely reuse the tests you have and ask the tool to build on the existing tests for you. Not only that, but when you come up with your tests in the end, right, the new tests which the tool creates, you can link it back to requirements, figure out what parts of my requirements are dependent on this and what really I can go back all the way to requirement, right?
So can those tests that are being generated, can they be simulated as well? Is it the same thing as the requirements-based test that you showed us right in the beginning, or is there any differences?
Absolutely. So we're still in simulation mode. We started off with ad hoc simulation. We did functional or input-output behavioral simulations. Again, these tests which we generate for you are simulation-based tests as well. So you can simulate these and actually validate or verify your result with the same, right? So that's for the green part, right? Going back to your earlier question, there is part of the model which yet shows up as red. And if you look at my objectives, my inspector over here, it says 2 out of 257 objectives are proven unsatisfiable, right? So there is a part of my model, right, which shows up in red. In this particular case, in test generation mode, what I'm saying is there is no way it is mathematically impossible for this modes.fail condition to ever be true, right? Again, we're using mathematical analysis techniques over here, and if the tool cannot do it, there's just no way this part is going to be true, which is to say that this particular transition is dead logic and will lead to redundant code if I were to generate code for this controller.
So it seems like you started out with the goal was to create test cases, but you also discovered sort of an error on the side.
Right. So you're right. So the goal is, incremental verification. You want to keep adding robustness at every step of the way. And part of finding these, running through test generation, we did identify some parts of our design which really there cannot be any test for, right? And at this point, I want to go back and buckle down with my design engineer because it requires some amount of knowledge of the design to figure out what exactly is it which is happening here, right? One way to backtrack is you can right click on a particular, this function, which is, in red. You can use requirements traceability to go back to my requirements, just like Siddharth showed you earlier. This is linked to an external requirements document. Requirements traceability also lets you link to different parts of MATLAB and Simulink blocks. So you can see that my particular function is also linked to a state within Stateflow, right? Let me zoom in here. What is happening here is that the power supply should turn off whenever my function is in, or my fan is in isolated mode of operation. But there is something within my power shutoff function, power supply shutoff function, which is overshadowing another part of my design. And hence I'm seeing this dead code or dead logic out here.
So essentially what you're able to point out is that there are two completely unrelated parts of your design, which you are able to now find out that one is overshadowing the other. Now, something like this would be really hard to catch in real life, right? If there are two things that are completely unrelated in completely separate functions.
And that is the main point which I'd like to make, right? This would be really, really hard to figure out if we didn't use this technology. You'd have to run or come up with your own set of test cases and figure out, you know what, I've written 100 of these, but I cannot figure out how to reach here. So I'm not saying you will not be able to detect such conditions, but typically customers detect these conditions either out in the field or really late in their design process. And this tool is helping you find and fix these earlier on, right? The fix is pretty simple in our case. I comment out part of my logic, which is overshadowing the other design. And I will do the same for the cooling system B as well. After making the fix, I want to run Simulink Design Verifier again. I'm generating tests on the model again. And this will go through the same process, right? It'll identify those objectives. It'll try to prove these objectives for me and generate tests for each of these condition and decision points, right? And in our case, we should see everything show up as green.
Okay. So, I guess, so just to recap, I mean, what are the things? So at this point, we're not in simulation. Right now, we're using mathematical methods to actually generate test cases to top off in some way, as you'd said earlier, to top off the test cases that we had functionally created. And now a user would probably go back and reuse these test cases in simulation, see how it behaves. And then if you change your model, you want to reuse the test cases over the model, run it on software as well, perhaps like in software in the loop mode, processor in the loop mode if you would need, and so on and so forth.
Absolutely. Absolutely. And again, all these test cases are simulatable, and again, it's adding value to model verification. You're still in the model, you've not yet generated code. All right, so to put that into perspective, let's go back into our presentation again, right? We covered three parts of verification, right? We talked about functional input-output testing. We talked about model coverage analysis and test generation to find, find all the parts within your model or generate tests for you and find design errors, right? The next part is, you're done with your software, right? You're pretty confident about your design. You feel good about it. You want to generate code for the same. So let me show you how we would do that.
And this code, again, you could generate for prototyping. You could put it on your prototype and use it for testing, but you could also generate it that could go onto your production hardware as well, right? I mean, we're not really saying that you don't need to be doing testing on the system or the prototype itself. You need to do that, but there's so much more analysis that you were able to do before any of your before any hardware was available to you.
Absolutely. So I'm back in my model. I've right-clicked and I can generate code for this particular subsystem.
So you're generating code, it seems like, for the PLC system over here, but there are some other options there as well. So for HDL and C++, what are those options?
So I'm really glad you mentioned that. Let me zoom in. You have the choice of generating PLC code, HDL code, which is for ASICs or FPGAs, if that's your end target, C or C++ code, if embedded coder, using an embedded coder tool. This is, of course, if you're targeting any embedded
microprocessor, I guess.
Microprocessor, right? In our particular case, I'm going to select PLC code, right? I want to generate structured text for my model. Let me right click and generate that. In fact, we have various optimizations available as well. If you have specific targets in mind, we'd be able to give you optimized code for those target applications. All right, so I've generated code. One way to view the code is through this HTML report, right? This is my structured text in my top right. Again, this is all auto-generated code. There is links. I can link back and forth. Basically, it's just an easy navigation within the report from my code to the model, right? As you can see, I can go back and forth between model and code. What you see on the bottom right is view only version of the model. You cannot simulate this. Again, this report was built for ease of design reviews. You want to explain to colleagues what you're doing or sharing your code.
So I think this becomes useful for me to understand what parts of my code relate to which particular parts of the model, right? But so this is a report, but in general, there must be this code that is being generated somewhere as well. We don't need to look at it right now, but you do generate this code as a physical file that can be included as part of the other designs as well, right?
Yes, this code is available standalone. You can package it up and give it to someone else as well. You don't need this report. It's just a nice way to view it. Yes, to your question, you can definitely view the code only if that's what you want.
So while we're on the topic of reports, for all the testing that you had done, generally I've seen our customers need to document their test results as well, or automate some of that testing and maybe tweak around the reports that they get as well, customize them to meet their company formats, add their logos and stuff. How much can we do any of that as well within our tools?
Yes, if you want to customize any of these reports, you can, using the Simulink report generator tool. A lot of the people, our customers we know, leverage the tool to kind of customize whatever they want from these reports. Out of the box, you get reports with each of these model verification steps. So you'd have these reports, the coverage analysis or code generation or test generation come with their own reports as well.
Okay, excellent.
So let's get back to the presentation mode to see if we can summarize where we are and what we've shown you.
So just to summarize, we started off with we looked at Simulink, which is an environment for modeling multi-domain systems. So we modeled the physical components, which is the cooling fans, the device that is generating heat as well. We then used Stateflow to create the logic, right, to model the logic. We did some interactive testing. Nishad showed us how to add more rigor to that. And then in the end, once we were sort of happy with the design that we had, we generated code that can be ported onto hardware for testing. And so you can test that in the loop as well. And then actually put it on a prototype and actually deploy it for your production systems as well. So hopefully through this presentation, we've given you a sense of the workflow that you would have for designing and verifying supervisory systems that are safety critical. Of course, there are more steps that you can do if you were to have more certification requirements. We have additional toolboxes that can talk about that as well, but we didn't plan to cover that in the scope of what we had today.
So Siddharth, one of the things which our customers ask us, right? I mean, how do you get started with a design? Say I'm familiar, I have my own design, supervisory control somewhere else. I'm pretty happy with it, but I see some value of model-based design and I want to start using it. You have any suggestions for them?
Right. So generally, when a new customer picks up this, we start with we have some techniques that we help them to say, focus on a small part of your system, right? Build that up using our tools. As your familiarity with our tools now increases and you're more comfortable with them, then replace some part of your system with that, the generated code from our system. And then you build upon it. So it's a very staged sort of incremental sort of process of how you include and build systems and gain familiarity with our tools. And that's kind of what we propose when our customers use. It's generally not a one-time fix.
And, in addition to that, we have different training offerings. MATLAB Central is a great community-based environment to learn more about our products. Product pages have webinars and videos you could use with getting started examples. And of course, feel free to reach out to Siddharth or myself if you have trouble getting started or you just want to learn more.
I would also just look at Google, search Google, because we have a ton of resources that we put out every year. Our documentation, we take a lot of pride in the quality of documentation that we put out for our tools. So that's all available freely on the web as well, which includes examples for you to look through. So looking through those, feel free to look and see some of the things the capabilities that we've talked about today.
All right. Thank you so much.
Yeah, that brings us to the end. Thank you so much.